Okay, hello everyone. In today's video, I would like to summarize paper, namely towards OpenSet deep networks. So this is actually a paper that try to tackle OpenSet problems or OpenSet recognition. So this is a little bit like an extension of the standard problem of a deep neural network. So firstly, I would like to discuss about what is OpenSet recognition. So basically, let's say that if we have three classes, let's say this is class A, B, and C. So we have, let's say, multiple of inputs like here. Okay, and it is connected to each other. Sorry for my bad drawing. So something like this. I hope you can get that this is neural network. So this neural networks is designed and trying to classify three different classes. But let's say that we have another class. Let's say this is class D or class E or F, for example. And then when we pass an image with class D, let's say we pass an image here, it will produce output probability based on these three output neurons. Either it will be overconfidence or misclassified. Overconfidence means that either one or two of these neurons will provide higher probability, let's say 0.8 or 0.9 or 0.7, and mispredictions means that it cannot detect that this is actually outside of a distribution that has been trained. So this is like extension of the closed set classifier that mostly we know in deep neural networks problems, specifically for the image recognition. So this is the paper that try to identify unseen classes using output layers called OpenMax. So these papers propose OpenMax to replace with the original softmax layers. So how it is work? So before we go there, there is a nice figure about what's happening in OpenMax. So as you can see in the x-axis, this is classes in ImageNet. And let's we pay attention to the baseball class. This is baseball class. And this is the original model and real images. So in the model and real images, we can see that mostly in the part of this one, in the baseball class, it provides high score of activation functions, which is illustrated in the green colors, and then low activation functions is in the darker blue colors. And if we see in the hammerhead, in the model and real image, activation functions mostly happen in the shock and wheels in this area. You can see here, which is makes sense that this is hammerhead shock. At the great white shock is also happen in the same activation functions. So we can see that two classes provide quite similar activation scores in the model and real images. And also in scuba diver is quite in many places, but not in the dogs area. So this one. Okay, let's try to erase all of them first. And when we can see on the falling images is something you can see here, example, which is actually we don't know what class is. And in the falling images, for the baseball, this one, activation function shows more score on the shock and wheels like this one, and a little bit on the baseball areas, but not like the original images or real images. In the fully image in the hammerhead shock, it also happens that the activation is not really full on the shock and walls area like this one. And in the falling of the great white shark shows also quite differently with the model, with the original model or real images. And in scuba diver also behave the same way. And in the open set classes, open set images is actually classes that is not in our distribution of the model. So it's actually the class that is not trained in the model, like this one. It's also provide similar behavior. You can see in this one, the open sets is quite active in the range of socks and walls. So this is in the left side. So let's move to the right hand side. So in the right hand side, there is two classes that we can see the performance of the OpenMax, which are baseball and hammerhead. So we move to the folding in open set. So in the folding, SM is actually softmax and OM is OpenMax. So in the softmax course, in the folding of the baseball, it provides perfect output distribution, perfect prediction, which is 1. And then, but if we see on the OpenMax is provide 0 value. And in the hammerhead is provide high confidence in the softmax, but in the OpenMax is provide 0 values. It's also happened with the OpenMax. You can see here that in the hammerhead, softmax provide 0.25, OpenMax 0.1, and this one OpenSet 0.15 is quite good actually. Provide lower confidence and OpenMax is 0.17. Okay, and if we move to the adversarial images, as you can see here, this is adversarial images is actually an image that try to change some pixel in the image, but actually still represents the classes, but unfortunately it is predicted as wrong classes. So for example, in the hammerhead, some pixels are changed or added. Change, but still the image of hammerhead we cannot tell in our eyes precisely, but in the model it predict differently. So from the hammerhead it predict as the scuba diver. So this is adversarial. And when we check on the right hand side, adversarial scuba diver softmax provide 0.32 and OpenMax 0.9, which is actually quite good for this one. 0.32 is scuba diver and 0.49 is for the unknown. And after blurring, OpenMax provide 0.79 for hammerhead. Okay, so we check on the how this OpenMax works. So as you can see that OpenMax utilize wearable distribution. So wearable distribution is type of distribution that give us much more flexibility compared to the Gaussian or normal distribution. If you look at the left hand side at these pictures, it has two parameters, lambda and k. When lambda is 1 and k is 5 here, you can see that it's similar with the Gaussian distribution. In Gaussian, we tend to use the mean and also the variance to specify the the width, of the Gaussian or normal distribution. But in this case, it's quite flexible. It provides a different curve of the distribution. So at this point, we utilize several numbers, total numbers of the distance between the mean of the activation factors of each class with the samples. So you can see here that it requires n largest distance to mean activation factors. So we need to specify these hyperparameters. Let's say if it is 5, so we have to calculate 5 largest distance for each new output activation factors. So at this point, this algorithm tries to fit with the wearable distribution. It will produce or output the wearable distribution, and is using a library called libmr, and it is available online. And as you can see that we have to get the activation factor for this for all the samples, and then for each class J, so we need to get the factors that is correctly classified. And after that, for all classes, we get the mean using the correctly classified factors, and then we try to fit using this mean and also using the samples that is correctly classified with the several numbers of largest distance to mean activation factors, and then we can get the wearable distribution. So each class has its own wearable distribution. So now how we can get that the model can reject that this is actually from unseen classes. So you can see from the algorithm tool, we need to, let's say if there's a sample X, and firstly we have to get the activation factors. So activation factors is actually the factors that we get before the output layers. So if we go back here, so we can see that this is output layers, and we can get the activation from this one, the activation factors. Okay, so we get the activation factors, we get the means of every classes, and we also have the wearable distribution of every classes. Okay, wearable distribution, and it also requires alpha, which is the number of top classes that we want to revise. So activation factors that we get from the models is actually will be revised by several numbers of top classes. So we need to specify these hyperparameters, and then we try to get the, what do you call that, this one, the SI, which is the sorting of the activation factors, and we let every classes has weight 1, and then for 1 to the number of top classes we get the weight. So every activation factors top alpha will get the weight based on this one, which is based on the wearable distribution, and then we revise the activation factors with that weight, and then we can get the new activation factors, which is this one, phi0. So phi0 shows that this is actually the unknown classes or unseen classes, and then this is actually just activation factors multiplied by 1 minus wi and x. And then we use these all factors with +1 +1 activation factors, and we put that into the softmax layers, and then we sort based on the highest to the lowest descending, and if it is actually provide 0 for the index of the softmax output, so we can say that this is actually samples from the unseen classes, or let's say the output probability is actually less than of epsilon, which is a threshold to reject unseen classes. So if we see the results, actually these models rely on the threshold, so we need to find a good threshold, and as you can see here that at 0.2 it provides a good result compared to the SoftMax. So this is OpenMax in the red colors and SoftMax on the blue colors. And this also show threshold is sensitive to the fooling samples and also open set samples, and we need to find the good threshold. And it's also quite sensitive of the tile size. As you can see that the optimal tile size is 20. As we increase the number of tile size, it can predict much better performance of the open set in terms of open set. But at the same time, it will sacrifice the closed set accuracy, which is just normal accuracy of the deep neural network, as you can see here. So 20 is the optimal value, and then alpha, which is the top classes that being revised in the OpenMax, is also quite sensitive, and it say that alpha with rank 10 is the optimal in this case with ImageNet dataset. So that's the summary of the papers of the towards open set deep networks, which replace SoftMax layers with the OpenMax by calibrating the activation factors based on the Wearable distribution. So actually this is good in terms of the ImageNet, but we still do not know the performance of the real-world applications, especially with the high resolution and much more complex images. Okay, thank you for watching.